Okay, so welcome to this Redux video. Today we'll be going back and tackling for a second time the definite integral or slash the trigonometric integral of 0 to pi over 2 of the fractional of tangent of x dx. So if you want to view the original video, the link will be in the description below. So this time this video will be a lot shorter slash condensed, and then the handwriting will be a lot more bigger and at the same time legible as well. So a lot of the process we'll be dealing with is, again, elementary calculus techniques, some infinite sums you'll see, and actually we got a bunch of couple special functions we'll be using to utilize evaluating this integral. And just to give this, since if you've already seen the video, you already know that the answer is actually going to be in terms with imaginary numbers, so some complex numbers going to be involved, and a lot of that interesting stuff. So I feel like this is one of my, favorite integrals to tackle as a hybrid of both trigonometric and dealing with fractional parts. So I feel like this one could actually deserves like a second chance for anybody, for especially new time viewers, especially back when this video was first uploaded. This was, the channel was relatively small at the time. So with that, let's actually jump right in. So let's, of course, gonna start this with a u sub. Let's suppose that we'll let u equals tangent of x. And we also have a dx differential. We want to substitute that back. So we'll have to do this so we get x on its own at first before we can differentiate both sides. So if I get this by itself, then that means I have that x is equal to the inverse tangent of u. Then if I differentiate both sides, I have that dx is equal to 1 divided by u squared plus 1 and then du. Okay, and so now we can actually substitute all that back in. So now our new integral, we're going to call this capital I. We'll let this be, so change our bounds. So I have that this is 0 for x. That means u is going to approach 0. And if I have pi over 2, then that means that's not defined, but actually as it approaches pi over 2, that's actually going to approach infinity. So with this, and now we actually can substitute this for the fractional of u, and then divided by u squared plus 1, and then du. Okay, so now before we continue further, I think we should actually go into a little bit just a basic definition of what a fractional of some variable is. So of course that's saying with the following formula that the fractional of u is equal to u minus the floor of u, where the floor of u is the greatest integer function such that the floor of u is equal to k, such that we have this compound inequality that k is less than or equal to u, which is strictly less than k plus 1 for all integers k. Now, of course, in a situation like this, if you want to be a little bit, nitpicky with it, you can say this is the natural numbers, especially dealing with our especially that we're dealing with the positive range. So not necessary, but you can just throw that out there anyway, because why not? So with that definition in mind, so let's actually replace the fractional of u with that formula as mentioned. And another thing I'm going to put down is that we're actually going to take this in terms of a limit. So I'll write this as the limit. We'll say this is going to approach capital N to infinity of the integral from 0 to capital N of u, subtract the floor of u, and then divided by u squared plus 1, and then du. Okay, so with this in mind, let's actually take things one step at a time, and then we'll split this into the, in terms of linearity. So the first thing we want to deal with is with the definite integral from 0 to capital N of u subtract u squared plus 1. So of course, this is very simple to see that you can actually just apply, u substitution. And so we'll have that this is by the antiderivative, we have that this is 1/2 multiplied by the natural log of 1 plus u squared. Doesn't matter how you write it, u squared plus 1 or 1 plus u squared. So the same thing in terms with the commutativity of the addition. So with that in mind, then we can evaluate this from 0 to capital N. And so if I plug in 0, so that means that's going to be 0. And put this back together, we have that this is the natural log of n squared plus 1 and then divided by 2. So with that in mind, so let's actually continue on and put this back into our capital I. So now so far we'll have that this is the natural log. So I also need to write this in terms of a limit. So the limit as capital N approaches infinity. Then now we have that this is the natural log of n squared, capital N squared plus 1 divided by 2. And then now subtract this with our integral from 0 to capital N of the floor of u and then divided by u squared plus 1 and then du. All right, and then close that off. All right, so now what we need to do is let's actually evaluate our floor function integral. But think about this in terms of how we're dealing this term-wise, because we're going from 0 to capital N, and we have the floor. So utilizing that definition, we can actually write this in terms of a sum. So I don't want to say infinite sum because we're taking this all the way up to capital N. So we're gonna, take into that, consideration. And because we're also dealing with as capital N approaches infinity, so infinity isn't really defined to be as, a specific number. It's actually just continuously goes on forever and ever. What I'll do in this situation for how we write our sum is I'm actually going to dial it back down a bit. So subtract one index down. So this won't change anything because yet we're still taking things, in terms of a limit. So in other words, to rewrite this, I have that, of course, this is the limit as capital N approaches infinity. Okay, so we're still doing the same thing. So ln of capital N squared plus 1, and then divided by 2. Then subtract this, so now we're gonna have our finite sum, so the upper index is gonna be capital N subtract 1, and then our index starting from k is equal to 0. Then we're gonna evaluate this from k to k plus 1 of k divided by u squared plus 1 and then du, okay? And then now to put this even further, that we can simply evaluate this. I'm actually just gonna move this to the next line to utilize some space. So continuing over here, we have that now this is the limit as capital N approaches infinity. So we're still gonna have the same thing. So natural log of capital N squared plus 1 divided by 2. Then afterwards, if this is the easy antiderivative, I'll just factor out the k. So that's just 1 divided by u squared plus 1. Antiderivative of that is basically just arctangent of k, or of u specifically. And then evaluate this from k plus 1 to k. And so now we'll have that the following is gonna be the finite sum capital N minus 1, then k is equal to 0 of, now let me actually put this in parentheses. So we'll have that and multiply the k as well, don't forget. So k times arctan of k plus 1, and then subtract with k multiplied with arctangent of k. And so with this in mind, now we want to ask ourselves, what do we do from here? So let's actually add a 0 term. So what I'm going to do here is specifically for the k that's associated with the arctan of k plus 1, I'm going to add and subtract a 0. Well, specifically add subtract 1, that's what I meant to say. So that means I have k plus 1 minus 1, that quantity multiplied by arctangent of k plus 1. Then distribute that so that we're dealing with a quantity of k plus 1 times arctangent of k plus 1, and then subtract with arctangent of k plus 1. What's the purpose of this? So let me actually first write this down full, and then we'll get to the specific details on that. So now that that's written out, so again, as I asked, what's the purpose of this? And you'll be asking yourself the same question. What is the purpose of this? You'll notice that specifically the k plus 1 arctangent k plus 1, and then subtract k times k, or multiply with arctangent of k, that's actually a telescoping series. And so what we're left with is just the first and the last term of the entire expansion. So let me write this telescope. And so what we do is, of course, if I plug in 0, that means I have 0 plus 1, so that means that's arctangent of 1, and then minus k, so that's going to be 0, so really that's just 0. But then everything onwards and so forth until the last term is going to be the only thing that actually appears. So the last term in this case is going to be the n minus 1 as we plug that in. So that means what's left is that this brace over here is actually going to converge to just n times arctangent of capital N. And then of course, I'll just write that as the plus arctangent with the series associated with that. So now we have that I is going to equal to, so the limit as n approaches infinity. So of course, we're still going to have the same thing. So ln of capital N squared plus 1 divided by 2. And then now we're just left with minus n, capital N, times arctan of capital N. And then now just leave this off with now, because it's minus, I'll distribute that as of now, plus, so the finite sum of n minus 1, or rather, we can actually take things one step further ahead and I'll actually readjust the sum. And so we get that this is just capital N, and then starting at k is equal to 1 of now just arctangent of k. So now another thing we're actually using is a nice little identity that, and I talked about this in past videos before, so that arctangent of k can be written as the same thing as pi divided by 2, subtract arctan of 1 divided by k. Okay, and so with this in mind, we're gonna actually, that's our goal in order to evaluate this infinite sum. Well, really it is an infinite sum, but we haven't taken the limit yet, so we're actually treating this as the finite sum for now. So now the finite sum we're dealing with, capital N, and then k is equal to 1 of arctan of k. Well, we just substitute this back in, so now this is going to be pi divided by 2, subtract arctan of 1 divided by k. And so to put this into perspective, so that means now we're going to have that the limit. So I know I forgot to write the limit over here, but that's fine. So the limit as capital N approaches infinity. So now if we actually take the sums, the finite sums of pi over 2, it's just capital N times pi over 2 plus so on, and then ends at the capital Nth term. So that means I have N, capital N times pi divided by 2. And then interestingly, if I were to take the limit as N approaches infinity, capital N approaches infinity for arctan of 1 over k, it actually diverges. There is no convergence for that. So to put this as a little bit of a trick, we're actually going to take this back forward to capital N, arctangent of capital N. Even if you were to take that limit as it approaches infinity, it's still divergent either way, but it's more of just a nice trick that we're actually going to utilize, that it'll clean some stuff up for further simplification. So go back to arctan of capital N. Okay, and so now going back further, then now I can actually just factor out the capital N. So the limit as capital N approaches infinity. So capital N multiplied by pi divided by 2, then subtract arctan of capital N. Okay, and so now in other words, we just use that same identity just like before, replace that. So now that just leaves us with the limit as capital N approaches infinity of n times. So now this is actually just going to be arctan of 1 divided by capital N. And so with this in mind, now all we have to do is just take that limit as capital N approaches infinity. But this isn't like easy to see because we actually have in the form of an indeterminate form. We can actually fix this up because the following preceding step, we're actually going to apply some L'Hopital's rule. So first, let's actually write this in form of like a rational function. So the limit as capital N approaches infinity. So that means I'll have arctan of 1 divided by capital N, and then on the bottom, I'll treat this as 1 divided by capital N. If I take that approaches infinity, I still get a 0 over 0 indeterminate form. Then continuing forward by L'Hopital's rule, I'll just take the derivative of both the numerator and the derivative of the denominator. So that means, well, before we get to that, I have to actually do a little bit of a substitution just to make things a little bit easier. So what we'll do is we'll let h equals 1 divided by n. So if that's the case, then I mean as n approaches positive infinity, that means h, I shouldn't write an arrow like that. I should just put that as a comma. Then h approaches 0. Okay, and so with this in mind, so now we'll have a new L'Hopital's, new limit in terms of that. So now there's going to be the limit as capital N approaches infinity, or rather, I made that mistake because now we're going to the world of h. So I have the limit as h approaches 0, then that means this is going to be arctan of h, and then divided by h. Now if I actually plug this for the limit, that means that's going to be 0 over 0. Then going back to over here, this should have been L'Hopital's rule over here. Let me specify that. Then I'll take the derivative of the numerator and denominator. So h is actually just going to be 1, so that's fine. So now I have the limit as h approaches 0 of 1 divided by h squared plus 1, which is indeed just going to equal 1. So that actually simplifies that down. So now let me actually erase all this out, and then we'll continue with the further simplification going forward. Okay, so just to redial it back a little, so far we have that I is equal to this following limit over here. And from the previous step we just did, we were trying to calculate what this is going to equal to. And we did indeed come down to that, which we said that was going to equal 1. And what I'll do here for n arctangent capital N, I'll actually write that back in terms of that finite sum that we did earlier when we were using that previous identity. So in other words, I could actually write this as the same thing. So of course, this is still the limit as capital N approaches infinity of ln. Well, actually first, because we already taken this limit, let me actually first write it as 1 plus, since that's already out of the way. So we have 1, then plus the limit as capital N approaches infinity of ln of capital N squared plus 1, and then divide by 2. Then convert this back into that finite sum that we were using from that identity earlier. So that means this is capital N, and then k is equal to 1 of arctan of 1 divided by k. And so with this, let's actually now keep going and move further, that we can actually replace this with using a representation series, since 1 over k is actually less than or equal to 1 for all k's for the natural numbers. So what we have is we're actually going to we're actually going to have a double sum in this situation. So I have 1, then plus the limit as capital N approaches infinity of, okay, so same thing, add ln of capital N squared plus 1 and then divided by 2. Then now we're going to have this double sum over here. So first I have the finite sum, so capital N, then k is equal to 1. And then now we're going to have the infinite sum, which is the series representation of the following of that's right here. So this is infinity, and then n is equal 0 of, now we have the alternating sum, so negative 1 to the power n, and then k to the power negative 2n plus 1. So that's the quantity inside there, and then divided by 2n plus 1. Okay, so here's the trick we're going to actually do here. So for n is equal 0, we're actually going to separate that out on its own. So in other words, I have, so the same thing, so 1 plus the limit as n approaches infinity. So everything is still the same thing the way it is so far. But now what we'll do here is now we have that this is actually going to be minus then the finite, so capital N as the index, k is equal to 1 of 1 divided by k, and then go back to the double sum as we from before. So capital N and then k is equal 1, and then the infinite sum, then now this is going to be n is equal to 1 of just the same thing from before. So here's what we're going to do. Notice that specifically over here, this is actually the capital Nth harmonic sum in terms of that definition. So what we'll do is let's actually observe the following. We're actually going to pay attention to these two terms with that limit as it approaches. And so this will actually make some things nice and interesting. So to observe the following over here, we see that the limit as, let me put a star over here, the limit as capital N approaches infinity of what we have now is the natural log of capital N squared plus 1 and then divided by 2, subtract with the capital Nth harmonic number, okay? So we know that asymptotically speaking that the Nth harmonic number of that, so that's actually the same thing as the natural log of capital N and then subtract the Euler-Mascheroni formula, I mean to say plus lowercase gamma, the Euler-Mascheroni constant. So in other words, we can actually do that substitution, substitute this back into the nth harmonic number. So we have the limit as capital N approaches infinity of this is ln of capital N squared plus 1 divided by 2. And then I have subtract the ln of capital N and then subtract the Euler-Mascheroni constant. Let's actually fix that up so that it gets a common denominator. So I have that will be 2 times the natural log of capital N divided by 2, and then minus the Euler-Mascheroni constant. Fix this up a bit to get the simplification. We'll have that the limit as capital N approaches infinity of the natural log of capital N squared plus 1 minus, now put that exponent back, so that means the natural log of capital N squared and then divided by 2, then subtract the Euler-Mascheroni constant. Then what you'll do here is that they're under subtraction, so I actually can use the natural log properties to say that I have the natural log of n squared plus 1 divided by n squared, or in other words, ln of 1 subtract 1 divided by n squared. Then if I take that limit, that thing is going to approach natural log of 1, then natural log of 1 is 0, and so this term is actually going to vanish, and so therefore we are just simply left with just the negative Euler-Mascheroni constant, negative lowercase gamma. So now to put everything back in together, so now our new capital I is going to be 1, and then we already evaluated this term over here, so now that's going to be a subtract the lowercase gamma, and so we're still left with our double sum that we need to calculate. And another step further is that I actually just took the limit as capital N approaches infinity, so that's why we're going to see both the infinity symbols from both those sums. And so what we'll do now is that by inspection that, well, both of these sums specifically, that they both converge uniformly. So what I can do here is I can actually just interchange these two sums. So I have 1 minus lowercase gamma and then subtract. So first I'll start off with the index for n equals 1. So now we have the infinite sum. N is equal 1 of negative 1 to the power n, then divided by 2n plus 1, and then multiply with the infinite sum at k is equal to 1 of 1 divided by k to the power 2n plus 1. You'll notice that specifically this is in terms of the definition of the Riemann zeta function. So continuing forward, this is going to be 1 minus lowercase gamma, then now minus. Now we're just left with just a single index of the infinite sum. So n is equal 1 of negative 1 to the power n, then multiplied by the Riemann zeta evaluated at 2n plus 1, and then divided by 2n plus 1. So here's where the fun part comes. So another special function we'll be using is the Digamma function, which is the derivative of the logarithmic, gamma function. So to put this into perspective, that we're actually going to derive some of these calculations that first, so let's actually change the different color for this one. First, we're going to deal with is the Digamma function. So the Digamma of 1 plus x, okay? So, well, actually, let me first do the minus first, since that was what I wrote in my notes. So minus x, and then that means in terms of that definition, so in other words, that's the same thing as lowercase gamma, well, the Taylor series representation of the Digamma function. So at this value, so we have that this is lowercase gamma, negative lowercase gamma, then minus the infinite sum at n is equal to 1 of the Riemann zeta at n plus 1, and then multiply by x to the power n. So if you were to expand this out, we have a nice little trick that we're actually going to do. So we're actually going to separate this out depending on how the terms are evaluated at specifically. So if I have n is equal 1, so that means this is going to be 2, and then that's going to be 1. If I do 2, then 2, and then, or 3, and then 2. So depending on the difference of these degrees and the values of the Riemann zeta function, we can actually separate this out such that it actually deals with the subtractions of the series. So now I have lowercase gamma, well, negative lowercase gamma, and then subtract. So first I'll have is infinity, or the infinite sum of n is equal to 1 of first the Riemann zeta of 2n, and then multiply by x to the power 2n minus 1. Then we subtract this with the infinite sum at n is equal 1 of the Riemann zeta of 2n plus 1, and then multiply by x to the power 2n. Okay, so now let's actually take things into another consideration for the Digamma of 1 plus x. In definition, so the same thing, so negative lowercase gamma, then minus the infinite sum at n is equal to 1 of the Riemann zeta of n plus 1, but now this is subtraction, so this is alternating for negative 1 to the power n and then x to the power n. Do that same thing in a similar fashion, so that means I have now this is negative lowercase gamma, so now actually this is going to be a plus, so the infinite sum at n is equal 1 of the Riemann zeta of 2n, then multiply by x to the power 2n minus 1, and then subtract with the infinite sum at n is equal 1 of the Riemann zeta of 2n plus 1, and then multiply by x to the power 2n. Okay, so that's all good. So what's nice is that now I'm actually going to combine these two together and then divide by 2. So Digamma of 1 plus x, and then plus Digamma of 1 minus x. Divide this by 2. So let's first add these two together. So let me actually underline this so you'll see where I'm going with this. So I'm adding these two together, so that means lowercase gamma, then lowercase gamma, so that means that'll be a minus 2 gamma divided by 2, so that means that'll leave us with a negative gamma. And so now if I add these two together, so they're actually going to cancel each other out, and if I add these two, they're subtract, so minus 2 times these infinite sum, and then divide by 2, so we're just left with just the singular of that. So now all that's left is minus the infinite sum at n is equal 1 of the Riemann zeta of 2n plus 1, and then multiply by x to the power 2n. Okay, so that's good. So now the next step is, you might be wondering, what do we do from here? So notice that by definition, the dilogarithm function, the Digamma function, dilogarithm, I get those two mixed up, that's in terms of the derivative of the natural logs of the Digamma functions, the logarithmic. So I'll just integrate both sides, and so that's a minus, so that'll change to a minus, and then that be the natural log of the Digamma of whatever input, subtract with that. That's based on that u substitution over here. So that means now, after performing all this and actually integrating this side, but also I'm just going to add the plus gamma, integrate that, so gamma x minus gamma x, add that to the other side. So now that'll just yield us with the natural log of, and then combining together with the natural log property, so I have natural log of gamma of 1 plus x, and then divided by gamma of 1 minus x, then we divide this by, then this is 2, and then add this with lowercase gamma of x, and then this is actually just going to equal to the negative infinite sum at n is equal 1 of, this is going to be the gamma, the Riemann zeta of 2n plus 1, then x to the power 2n plus 1, then divided by 2n plus 1. Okay, and so now how to continue forward from here, that we're actually going to now suppose that we actually substitute x being I. So let me first get rid of this side of the board and then we can continue forward. So we let x equals I. So now putting this back together, so now I'll have the natural log of the gamma of 1 plus I, and then divided by gamma of 1 subtract I, okay, and then so divided by 2, and so plus lowercase gamma of I, and then set that equal to. So now what I'll do is I'll actually factor out the I to the power 1 outside of that, so now I have a minus I, and then multiply by the infinite sum, n is equal to 1 of the Riemann zeta of 2n plus 1, then to the power, or multiply by I to the power 2n, and then divided by 2n plus 1. So a little interesting fact that we know that when it comes to the imaginary power units, that I to the power 2n is the same thing as negative 1 to the power n, so I'll substitute that back in. So that means now that zeta function over here is that, and another thing I'll do is I actually divide the negative I to both sides as well, but I'll get that once I put the Riemann zeta, that final calculation down. So the Riemann zeta or the infinite sum at n is equal to 1 to infinity of the Riemann zeta of 2n plus 1. Well, now it's I to the power 2n. We said that that was negative 1 to the power n, so let me actually write that one first. So negative 1 to the power n, and then the Riemann zeta of 2n plus 1, then divided by 2n plus 1, therefore is going to equal 2, so divide the negative I to both sides, so I have negative ln of gamma of 1 plus I, and then divided by gamma of 1 subtract I, and then divided by 2i, and if you want to, just multiply the I to both the top and bottom, so that means that would actually just cancel out to be a positive, so minus gamma. And so to finish everything off that from earlier, I have 1 subtract gamma, and then minus this entire thing over here, and then you'll notice that the gammas are actually going to cancel each other out, so therefore capital I, therefore the final answer is going to equal to 1, and then subtract, since I just multiplied the i's to both the numerator and denominator, so minus, so I just write this as I multiplied by the ln of gamma of 1 plus I, and then divided by gamma of 1 subtract I, and then this being divided by 2. And so therefore that's actually the final answer to our fractional integral, well, the fractional of tangent of x. So as long as one notation you added, it actually make things a little bit harder. Otherwise, if this was just the integral of tangent of x, that might have been a little bit easier, but just putting that one operation in just changes everything in life, when it comes to math. So there we have it. So yeah, that's pretty cool if you ask me.